Hi, this is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver my lecture 23rd on the course of the strength of materials, and this course is developed under the National Program on Technological Enhanced Learning. Prior to start this lecture, I would like to refresh your previous concept, because you see we are going to use those concepts in this particular lecture. Like in last lecture we have discussed about that if we have a object, or if we have in a kind of any bar, this prismatic bar or kind of that, and if you are saying that there is a change in the dimensional of a particular in the longitudinal as well as in like the this lateral directions, then we can simply termed as this particular substance as a beam. Like you see, like we said, actually if whatever this, either we can say the thickness or the diameter in the lateral direction is very thin as compared to, or very small as compared to the length of the beam or the longitudinal dimension, then we are defined that part as a beam. So you see here we defined the beam in many ways, and then you see we categorize the beam by like the various the categories are there. In that, first we define that actually if we have a beam, the simple beam, then we can say the beam is either of the straight beam or then the beam is of a curved beam. And if we want to analyze those beams under the application of any force, then you see we found that both the straight beam as well as the curved beam has a different theory altogether, because you see in the curved beam we have a curvature theory, and then you see the corresponding the bending stresses or the shearing stresses will be coming. So that part you see we are going to discuss later on. Then we discussed that actually if we can classify the two main types of beam, first based on what kind of supports are. So first we found that actually if one end is rigid and other end is free, that means you see the cantilever, or we can say the beam which is supported by one end rigidly, we termed as the cantilever. And you see because of the rigid support, they won't allow this kind of beam either in terms of the rotation or the translation. So this beam is of having a different kind of nature, and then you see would like to see that if the kind of forces are applying, then actually what will happen. And the second kind of beam, again based on what supporters are there. So we can say that actually if the simply supported beam is there, that means you see if the two pin joints are there at the extreme end of the kind of beam, then always the reaction forces are there, and the reaction forces are in both mutually perpendicular direction, in x as well as the y direction. And then you see we also found that actually if this pin joint, or we can say the pinned this whatever the pins are there, and if they have a rollers, that means you see we are allowing this beam to move in x direction. This is also kind of a cantilever beam with the roller supporter in the pin joint. So you see here in that we found that only we have a reaction force which is vertically upward direction. So these two types of beams we can say simply based on that how these supporters are. Then we also discussed that actually we can also classify this beam based on what kind of loadings are there. So we found that actually if the loading is just you see in the entire length of beam only at some portion, or we can say that actually at some of the effective area just where the loads are there, and they are either the hanger side, or we can say they are either just actually concentrated parts are there, these kind of loads are known as either the concentrated load, or we can say that since the effective area under these loads are very tiny as compared to this the total length of the beam, so we can say these are the point loads. So generally you see if we are classifying this kind of concentrated load, or where the effective area is very small, we are always using the point load, and we are always showing these kind of point loads by an arrow. That actually because they are concentrated, so you see they are coming in terms of 10 Newton, 20 Newton, 100 Newton like that, and they are always applying either vertically downward or vertically upward. Because you see actually if as we discussed about the definition of cantilever, we found that whatever the load application is there, they are always perpendicular to the axis of the beam. So you see here either it will come on vertically upward direction or vertically downward direction, because you see we have a longitudinal axis as the horizontal. So this was you see the one kind of loading. Then we found the another kind of loading, that in which the load is distributed over a short span of a beam, or we can say the entire span of the beam. So if it is distributed in a short span of beam, then we found that it is nothing but equals to the this non-uniform distributed load. That means you see, like only one part is affected over which these loadings are there. This is not the point load, because you see they are already spread it out over a certain part of the beam. So we can say this is the distributed load but non-uniform. But if I am saying that this whole this whatever the load conditions are there, and if it is spreaded all across the beam, then it was the this uniform distributed load, or generally we are termed as the UDL. So uniform distributed load is always presented over the entire length of the beam, and whatever the kind of supports are there, respective of whether it is a cantilever beam or a simply supported beam, these kind of analysis is always important. So you see here, if you are talking about the non-uniform distributed load, always, or UDL, uniform distributed load, always we are not saying that it is 10 kilonewton or like the 100 kilonewton or 10 newton like that. It is always be termed as 10 newton per millimeter. That means you see the effectiveness, or we can say that the magnitude of these kind of loads are having a constant part like 10 newton, but since they are like spreading in a particular millimeter or centimeter, or even like sometimes we can say if it is this beam is of this kind, you see like where the bridges are there, we can say in terms of the kilometer also. So if we are talking in that term, then we found that what is the rate of loading is. So always you see, if we are talking about the non-uniform distributed load or uniform distributed load, we always termed by newton per millimeter or kilonewton per millimeter or whatever like that. So always you see we can simply distribute these kind of beams in these two categories. And the third category was there, in which always we found that actually when we have a dam where this water distribution is not uniform, at a particular end we have the like the maximum load condition, at the other end we have a very minute, or we can say the negligible kind of load conditions are there. So we can termed as a triangular loading. So in that you see we would like to find it out that if we want to find it out the what is the impact is there. So in that we would like to see that what exactly the total impact is there. That means where is the center of mass of this kind of loading is, and then once you locate the center of mass for this kind of non-uniform distributed, or we can just you see like the triangular loading is there, once you locate that point, then you can easily find it out that actually what is the overall impact is there, because at one point of like at one corner of this beam we don't have any loading, but at another corner of the beam we have the full loading. So you see we will discuss in like in this lecture that actually what the exact impacts are. In the last section I told you that like whenever the kind of loading is there on a beam, irrespective of whether it is a simply supported beam or a cantilever beam, always our main intention is that how these, because like when the loading is there, then bendings are there, so how this bending is forming in that, and you see we would like to show on a diagram. So these diagrams are known as the bending moment diagram, because you see it like these different loadings are there, the different sections, and the reactions are there from the joint or supporters. So how they are playing like on the entire length of beam, our main like interest is just to see the what is the bending moments are there, and we would like to show these kind of bending moments on a bending moment diagram. Second, you see whenever the bending moments are there, or we can say the bending is taking place on a beam, altogether you see at a particular section or in the entire like the sections of the beam, we just want to see that how this shearing is taking place, because you see one load is acting on top of that towards the vertical direction, the reaction is going from bottom to upward direction, so always the shearing is there. Then we would like to see that what exactly the shear force diagram is, and then what is the relation in between this bending moment as well as the shear force diagram. So these all you see like the kind of technical terms which we used here, we would like to see what the impact is there as well as far as this cantilever or simply supported beam is concerned. So here you see in this lecture we would be starting with this bending moment and shear force diagram, and then we would like to draw for different kind of load conditions as well as different kinds of beam also. So here you see the concept of the shear force and the bending moment in the beams. First of all, when the beam is loaded in some arbitrary manner, whatever you see like it is loaded in terms of a point load, or like the UDL, uniformly distributed loader, or non-uniformly distributed loader, whatever the kind of loading is there, arbitrary manner, you see the internal forces and the moments are developed. Basically definitely see whenever we apply something, the internal resistances are coming out from like the beams, or we can say that the internal intensities are there, and due to the internal intensity of these forces the shearings are there, and these kind of shearings are always bending as well as the shearing stresses. So this internal moment and the internal forces and the moments are developed, and these like the terms of shear forces and the bending moments come into the picture, which are helpful to analyze the beams further. So you see here these two are the like the dominating parameters, though you see there are other impacts, but these two are the key features to analyze any kind of beam. So if you would like to design a beam, then we have to see that actually how these these bending moment as well as the shear forces are generating in the beam, and how we can analyze and which section is prominating by these kind of either the bending moment as well as the shear forces. So now our main thing is just to consider the beam, as shown in this figure, that we have a beam, and in this beam we have the two supporters. So here you see this beam which is having the length L is supported at these two corners. One is the overhang part is there, so this end is free and it is supported by that. So this is the overhang portion, and this is exactly supported at the end. So if we see this figure, we'll find that there are two reactions the two reaction forces are coming from these two joints in the vertical upward direction, as I told you earlier, and then we have the three different forces P1, P2 and P3, and they are just acting on the downward direction. So this beam is supporting by the loads P1, P2 and P3, and simply supported beams are there because you see the two different joints are there, and these two contacting points where the supporters are there, we have the two reactions as I shown in the previous diagram, R1 and R2. Now you see we just assume that the beam is to divided into just an imaginary way by AA section. As you can see this one, we just divide this into the two category. We would like to see that how this force distribution is there, and under these forces you see the applied load, reactions and whatever like that, how the stresses are being generated, or we can say induces in this particular beam, and how we can do the analysis. So for that we just want to make it easy, easy analysis. So what we did here, we simply cut the section at AA. So if you see this beam carefully, then you will find that at the left hand corner of the beam, what we have the two different forces which are coming from upward direction. These are P1 and P2, and there is one force, reaction force, which is going up in upward direction. So if you just see the feasibility of these forces, then you will find that I am just talking about the left hand side only. So you will find that we have a reaction force on top of direction, we have a load on bottom direction. So there is a shearing is there. So definitely if you see on this portion, just see on that particular part, if you see this portion or this portion, we have a shearing action, and due to that this beam will go in this kind of bending moment. So always you see we have a bending as well as shearing together because of these load condition, either the left side, and if you just see on the right side also, you will find that this reaction will just move this this beam in upward direction, and this load will tend to move in the downward direction. So we have a shearing action, and due to this shearing action, the affected area of this one, or we can say the affected length of this one, and also you see due to that it will always try to bend in this direction. So you see we have the bending action as well as the shearing action together. So we would like to analyze both of them, you see the bending as well as the shear in a separate manner, and then we would like to combine both the thing as well for our analysis, that what exactly the interaction is there in between the bending moment as well as the shear stresses. So now you see again we would like to see that what exactly is happening. So let us assume that the resultant of the load as well as the reactions, the loads P1, P2, P3 as well as the reaction R1 and R2 to the left hand corner of AA. As I told you, you see there were in that the two forces were there, P1 and P2, and the reaction was there in R1, is just F1. So you see the resultant, as I show you and in dotted one, is just F1 is there, the resultant force vertically upward which is acting, and since the entire beam is to remain in equilibrium manner, because you see as I told you for any kind of analysis in the strength of material subject, whatever the forces are there, even they are applying, and if we are saying that our object is just stationary, that means whatever the forces they are acting from outside and whatever the forces which are coming from the inside, that means the reactive forces, they are well balanced, and we can say that the system is in equilibrium. So here also we are assuming the similar kind of situation. that we are applying the forces from top of direction P1, P2, P3 like in the downward direction, and the reactions are there from the downward direction towards the upward way. So both are well balanced and the beam is in the equilibrium position in the left as well as the right corner of AA dash line. So if we go for that, then we will find that the resultant of the forces of the right direction of AA must be also F, which will act in the downward direction. So you see here, if we just cut as I shown you that we are simply cutting the beam in AA section. So whatever the forces which are generating on left hand side, as just discussed, that actually the resultant is F1 which is acting upward direction. Similarly, the complementary part will come just to balance this beam, which is equal and opposite to this particular force. So we have the resultant part of F also, which is in the right one, this right direction of AA section, which will be always equal in magnitude F and act in the downward direction. So that's why you see we can say that this beam under the application of these forces with the reaction forces or applied forces, it is well equilibrium manner. So this force F, which we are saying that the resultant force is nothing but the shearing force, because you see these are the resultant this force is the resultant due to P1, P2 from upward direction and the reaction force from the downward direction. So you see here this always shearing this beam, we can say that this is nothing but the shear force, and the shearing force at any section, whatever we can say the cross section of beam, represent the tendency of the portion of the particular beam on one side of the section to just like the sliding part, or we can say the shear laterally relative to the another portion. That means you see like it is just always going in the lateral direction just to give an impact. That's what you see generally. If you just go to the previous sections which we discussed about the shear part, shearing is always coming not in the axial way, it is a plane stress which is always acting right from like the circumferential part. So here also if you go for that, we have a beam and this shearing is always going in the lateral direction to one part to another part, and it has a direct impact if you take any cross section, and we discussed many cross sections, like we have either a rectangular cross section or a circular cross section, or even we have a I section beam. In all of the sections, you see, you take any cross section, you will find that whatever the shearing forces are coming, they have a direct impact and they are going in the lateral direction relative to one portion to the another portion of a beam. So you see now we are simply in a position to define the shear force, and at any cross section of a beam, the shear force is the algebraic sum of all the lateral components of the forces acting on either side of the cross section. So you see here, as I told you that what we are doing here, we are simply taking like just in the previous action we are taking the two portion only. So even if you divide the this beam in the many cross sections, means many like the segments, and if you are taking like the this shearing force at one segment by the application of force, simply sum up those, linearly sum up those forces, and you will get the overall impact of these shearing forces on the beam. So you see here we are saying that this is the algebraic sum, that means it is a linear sum is there of these forces, because they are applying all across the beam, and you will find that since we have a same cross section of a beam, so they have like they are always setting up in this beam in a very uniform way. Now you see our main interest is that since the shearing forces are always there due to the application of any kind of force on a beam, so our intention is that how to analyze that. So for that, you see what we have done, we simply set up that certain sign conventions are there for this kind of shearing forces, whether you see it is going in the resultant is upward or resultant is downward. We just want to give certain like the notation, so that if you want to compute, because what we are doing here, we are simply taking the algebraic sum. So you see whatever the directions are there, we just want to compute all those in the linear way. So our first focus is that what is the sign conventions are there for these kind of shearing forces. So you see the usual sign conventions we simply categorize into two main figures. So figure 2 is simply showing that if we have a resultant force on left hand direction in upward direction, that means you see the resultant force which is upward direction, and towards you see the left hand side of any cross section is a positive shear force. So if you see shearing force, the resultant shearing force on left side of any beam, the cross section, you see if I am saying that this is the AA section and the resultant is going in upward direction, and on the left hand side you see the resultant force is going in the like the downward direction, always we are going for the positive shear force. Just keep this thing in your mind that whatever the like these point applications are there and reaction is going on top topward direction and the force applied is in the downward direction, this side whatever the shearing is coming in between this section is the positive shearing force. So you see here, we have now just denoted that one sign, that if this kind of force applications are there, because you see the basic definition of force is what is the point of application of the this force is. So how they are attracting, or we can say how they are joining this particular point, this is the main criteria here. So here if it is going in this way, always it is a positive, and vice versa. You see if it is going, that means you see if on the left hand portion, if this resultant force is going downward direction, and on the right hand portion if the resultant force is going in upward direction, then we have a negative shear force. So you see here, if you want to draw any shear force diagram, or if you want to compute the algebraic sum of these shearing forces at different segments, if you see the resultant force in which this on the left hand side you see it is going to upward direction, and the right hand side if it is going the downward direction, just put the positive shear force plus F, and you see in the another section of that, if the resultant force is coming in the downward direction on the left side, and on the right side if it is going upward direction, then you just take the minus F, or we can say the minus V, or the negative shear force. So this is the sign convention for the shear forces, well, respective of even for a entire length of the this beam, cantilever or simply supported beam, if it is under the application of various forces from the downward as well as the upward, we just want to see that what is the feasible situation is there, that means what is the resultant is coming out of these forces, and due to that we can simply denote that whether it is a plus F or minus F, or generally we are denoting these shearing forces by V also sometimes. So we can say that whether it is a plus V, minus V, or what. So corresponding changes will come in the in this summation, and the net resultant will come on this particular cantilever or simply supported beam, and we can say that the total impact of the shearing forces are like that. So here you see now we just analyze those for shearing forces, but you see as I told you, due to these application of forces we have the bending also. So now we would like to see that how this bending moment will occur in this particular beam. So now again we would like to go for the previous case. So you can see on your screen that we have a figure, same like the cantilever beam with these two supports, and we have the same these three loads are there. So you see here what we have these three supports P1, P2 and P3, and we have the reaction forces R1 and R2. So due to that, now again what we want to do here, we just want to see that what is the bending moment, because you have already analyzed the shearing forces. Now our intention to see that what is the nature of the bending moment is. So for that again what we did here, we simply cut the section here by AA. So we have this section cut AA, we have a left portion, we have a right portion from this AA. So now if you go for the left portion, then you see we have the two main this point loads are there on top of that. So these 2 point P1 and P2s are there, which are acting to the downward direction, and we have a resultant which is upward direction. So if you see the real feasible situation here, what the resultant is, the resultant means you see in terms of bending, these two forces will tend to move this beam in the downward direction. So you see the resultant will come towards, they are pushing into the downward direction, but in between these two means the location of these point loads are different, they are not exactly on the same position. And in between these two forces what we have a point load which is acting in the upward direction. So you see if you go from the, now look at from the this AA section. So if you look at from this position, you will find that this beam, the overall resultant of this beam will tend to move in this direction. So you see here the dotted line which clearly shows you that this is the tending position of this bending moment is. So we have a bending moment M, and the direction is showing in this way. Similarly, if you go for the right direction, then again you will find that we have a reaction from bottom, the bottom part at this position, and we have this P1 is there on this towards the downward direction. So if you go for the overall impact, then you will find that we have a bending moment which is going in a upward direction, and the tendency of this kind of thing is this which can be easily shown by this dotted line, and we have a M magnitude of these things. So you see here, we have a bending moment which is going in this direction. So, this direction is there. So, it means that actually this overall impact of these forces on a beam will gives you the overall this bending moment in this particular cross section. So, now you see we would like to analyze that part. So, again you see all those things, it is pretty clear that actually we have like the P1, P2, P3 forces are there, and these reactions are there in this particular figure, like all those things. And now we just want to again cut the section which we did it, and in a similar manner again what we did here, we just want to see that what is the overall impacts are there of these forces in the left hand side, and what are the overall impacts are there of these forces on the right direction. And now you see here we found that the reactions in these sections in the particular left sections, the overall impact is coming in the clockwise direction. You see this part. So, you see whatever the tendency of the beam is there, it will tend to move in a clockwise direction. So, similar way you see we just want to make this particular beam in an equilibrium manner. So, what will happen, you see the complementary this kind of bending moment will be formed in the another section to make the beam equilibrium. So, automatically you see on the other side the bending moment will be generated because of the application of force, and this will help to be have the same magnitude but in the counterclockwise direction. So, you see that is what this is the termed bending moments are there, and we can say that now we would like to see that whether if you see the force under this force application, whether this bending moment is going in this direction or in this direction. That means you see in the upward direction or in the downward direction. So, accordingly our main focus will be there, that how the bending this beam will be reacted on this kind of bending moment. And generally you see we are termed as this bending moment as a m, or generally we are writing b dot m dot is a usual name of this bending moment. So, now you see here as usual which we defined the sign convention for shearing forces, here we would like to define the sign convention for the bending moment. So, for that you see the bending moment, again as I told you in the previous section that what we have on the left hand side of this AA section, you can see on this particular diagram on the left hand side. Now, if whatever the resultant of the forces are coming, if they just tend to move this beam in the clockwise direction, on the right hand side they are just tend to move this beam in the counterclockwise direction, we are saying that this is the positive bending moment. So, means you see if we have the resultant bending moment under the application of all these forces in the upward direction, that means you see both are going in upward direction, it is the positive bending moment. And due to the resultant of all these forces on a beam, if they just tend to move in a this you see on the left hand side, if they are just moving in a counterclockwise direction, and the right hand side if it is moving in a clockwise direction, to balance those things, if we have the tendency of the total beam in this direction, we can say that this is the negative bending moment. So, you see sometimes the term this sagging and hogging are generally used for positive and negative bending moment. So, you see the sagging termed is, sagging means you see it is the as per the shape itself, the sagging means the positive bending moment, and hogging means you see in this particular shape. So, generally we are termed as the negative bending moment. So, you see here now we have the sign convention for shear force, we have the sign convention for bending moment, as well as the shear force sign convention confirm. As far as shear force sign convention is concerned, we are saying that this and this is the positive direction, this and this is the negative direction for shear force. As far as as well as this bending moment is concerned, the sign convention, if it is in the the sagging mode, that means you see in this mode we are saying that the positive bending moment. If it is going in this direction, we are saying means the hogging direction, we are saying that it's a negative bending moment. So, just keep these the direction in your mind, and then you see corresponding numerical problems can be easily solved, or we can say that we are taking these signs for our the just algebraic sum of these, either the shear force as well as the bending moment. Now, you see here we would like to see that actually after putting those sign conventions, now how they will act, that means what is the bending moment as well as the shear force diagram is. And then you see here the diagram which illustrate the variation of the bending moment and the shear force values along the length of the total beam for any fixed loading condition would be helpful to analyze the beam further. That means, you see, now we would like to see that under these application of the forces, how like the shearing forces are varying. It is, see, for a particular section you must find that it is positive. After the adjacent to that portion, you will find sometimes the negative. So how the variation is there of the shear forces, or what kind of variations are there of the bending moment, and what the resultant is there. And then you see, after getting the resultant, what is the interaction is there in between those like the shear force and the bending moment. This is the matter of concern, and we would like to see the total impact of those things. Thus a shear force diagram is a graphical plot or a graphical representation which depicts how the internal shear force, the F, you see, which we shown that the resultant shear force on the left as well as the right direction varies along the length of the beam. And if you see that, like in the next figure, you see if X denotes the length of a beam, then F is a function of length. That means, you see, always if we are saying that if the concerned portion or the effective portion under which these forces are acting, if it is X, then how they are acting. So you see here in the next diagram, I am going to show you that actually what the shear force is there, but shear force is a function of the X, and we will see the effect of. Similarly, a bending moment diagram is also a graphical plot, or we can say a graphical presentation which depicts how the internal bending moment M or B dot M varies along the length of beam. And again, you see, we are saying that since like we are taking the individual sections of this beam, so M is also a function of X. So now here you see, these kind of actions which we found that whether the shearing force or the bending moment, since they are the function of M, so how they will vary, now it is our matter of concern. So we would like to first set up the basic relationship between the rate of loading, shear force and the bending moment, because whatever the rate of loading or the kind of loads are there, the point load, even the concentrated load, due to that like the shear forces are generated in those cantilever beam or the simply supported beam, and due to that the bending moments are there. So now our main intention is that what the relations are there in between the shear force, bending moment and these kind of loadings are. So for that, the construction of the shear force diagram and bending moment diagram is really the simplified way. Just if the relationship among the load, shear force and the this bending moment is stabilized. So once you have as we discussed, we have either a cantilever beam or we have either a simply supported beam, and on that also if we have a point load, so only just as I shown you in the previous figure, that only the point loads are there, P1, P2, P3, under which and then you see the reaction forces are there. They are also in terms of the point loads which are acting on the vertical direction. So under these load conditions, what is the real impacts are there, and what the relations are there, the mathematical relations in between the force, applied force, and whatever the resultant shear forces are coming for individual sections, and then you see what are the bending moments in those particular sections. So now we would like to make we would like to set up the relations for this kind of thing, but it depends that what kind of loadings are. For point loadings are there, or we have this UDL, the uniformly distributed load or non-uniform distributed load. And other thing, you see, whether we are taking a cantilever beam or whether we are taking the simply supported beam, because you see the nature of the reactions are coming from the kind of supports. So you see, whatever the forces are coming from the external side and whatever the forces which are generating inside, we would like to set up the relations. So basically what we are doing here, we are simply trying to set up the relations with the using of what the physics of the beam is. So let us consider a simply supported beam. So now you see we are taking a simple case of a beam which is a simply supported beam. The total length of the beam is a, L, I am saying that, and we are simply notating A and B carrying a uniform distributed load. So here you see we are not taking the point load as we discussed in the previous case. We have a UDL, so uniformly distributed load, and always you see we are showing the UDL by whatever the W per unit length, so kilonewton per meter or whatever you see per unit length. And let us imagine to cut a short just slice. You see what we are doing here, we just want to focus that what is the overall impact is there. So for that, just cut a slice or cut the short portion of length dx, just cut out from that loaded part at a distance x, where you see we have the origin. So what we did here, we are starting from a point which we are saying that the origin is there, and from x distance we simply cut the portion, and we just want to analyze that under these application. That means you see under this rate of loading, what the kind of the shear stresses and what the kind of bending moment is. So now here this diagram is. So what we have the entire length of beam, this and of this entire length of beam, this rate of loading is that means you see we have a UDL, uniformly distributed load, and this load you see here we have the maximum intensity of this loading, and here we have the minimum intensity of loading. And you see like this load is just varying all across the entirely like length of beam. So we have, this is the uniform distributed load, UDL is there, and then at these 2 points what we have the simply supported beam. So the reactions are coming from these 2 beams in the upward direction. So you see here these 2 upward directions are there, and now as per we discussed, what we are going to do here, we are simply taking like the small section of that just to see that how these shearing forces as well as the bending actions are taking place on this particular beam. So for that, our just for study, you see we are simply cutting this portion. So this circle shows you our main interest, or we would like to focus on this particular portion which has a distance x from the origin. So this is our origin, you see, and this is the x. So this length of the beam is x, and you see we are taking the portion of dx. So this length, the extreme end of this is x plus dx. So total like the length in terms of the horizontal way is just dx. So now we would like to see that under the dx section how these forces, or we can say these due to these this uniform distributed loading, how this shearing action and the bending will taken place. So you see here, as we discussed, let us like detach the portion of the beam as well as like just draw its free body diagram. So just concern on that particular force. We have a small portion. In the small portion, as I told you, what we have a simple like the length which is dx. So once you take this dx, and from the origin how much distance is there, this is the x. So the total distance is x plus dx, and then you see like so the center point at which the overall, as I told you in the previous section, that if we have a UDL, we would like to see that where is the center of mass is acted, that means what is the overall impact of this loading is. So the overall impact of this loading is coming from this direction which is going in the downward part. So at this particular point C, we can say that this loading is coming towards the downward direction. So now our main intention is coming in terms of the rate of loading. So what is the rate of loading? By this distance delta x, you will have the load. So W into dx will be the applied load which is acted on this point. Again focus this, the location you can easily find it out, that this is the C location where this point of like the center of mass is acted, and at the center of mass you see always the load is coming towards the downward direction because of the nature, and the magnitude is W into dx. So since this dx is there and this W is varying the rate of loading, so W into dx will give you the magnitude of load. Now you see what we have the reaction forces which are coming from downward direction. We have this W into dx, this is the magnitude of the load which is going towards the downward direction. So now if we are cutting the portion on the left hand side as well as on the right hand side, we have 2 different like the shearing forces as well as we have 2 different bending moments also. So now you see, just go to the left hand portion, what we have the shearing, this reaction force which is going on upward direction, the W into delta x is the total load which is coming in the downward direction. So you see this is the this notation is there. So as you go with the convention of this notation, you will find that what we have a positive shearing force, or we can say the resultant force. You can see the diagram, this F is going in upward direction, and if you go on the other side portion, so F plus dF is going in this direction. So total impact, that means you see it is going in this direction, the total impact of the shearing force is in this direction, we have a positive shear force. Now you see we would like to see that what this bending moment will behave. So if you see the resultant of the bending moment, which is you see like on the left hand force, the bending, this whatever you see the load is coming here and the reaction forces are going in this direction. So they have a tendency to bend this particular like the beam in this clockwise direction. So obviously you see on the other direction it will be the counterclockwise direction, and after a dx situation, what is the magnitude? The magnitude is m plus dm. So you see here this m plus dm will move in this way, m is moving this way clockwise and counterclockwise. So we have a sagging situation. So again you see what under these loading condition W into dx, and under these you see the reaction forces, we have a positive shear and the same time we have a positive bending moment. So you see here again the forces acting on a free body diagram, just you see detached the portion is loaded beam are just following. The shearing forces on the left hand side is F, the shearing forces on right hand direction is F plus dF, and you see since the cross section of the cross sectional length is x and dx is there, so corresponding changes are there. So the bending moment section at x as well as x plus dx section, that means this left as well as the right hand direction is m and m plus d, this dm, just the small section is there. So forces due to the external loading, this Wf you see is the mean rate, or we can say the rate of loading is there, and if Wx is the total load is there. So they are acting at a center C as I shown you in the previous diagram, and if this loading is assumed to be, and obviously we are assuming that it is a this UDL, that means uniformly distributed load, then it has a overall impact on a point C, which is nothing but equals to W into dx as I told you, and the small element must be in the equilibrium position, because whatever the forces they are coming on the left as well as on the right direction, or whatever the bending moments are coming as in the left as well as in the right direction, they are simply counterbalancing to each other. So definitely we can say that this section is in a balanced condition. And after applying, but again keep this thing in your mind that whatever the forces they are coming, the resultant forces on x direction, the resultant forces F plus dF in the x plus dx direction, they are in this section. So we have a positive shear force, and as well as you see as well this bending moment, it is this m is going in a clockwise direction, m plus dm is going in an anti-clockwise direction. So this is a sagging condition, and what we have a positive bending moment. So with the consideration of this plus and minus sign, now we would like to analyze those things. So come to this feature, that what we have at this extreme end, we have m plus this m is the bending moment, which is tending to this this particular beam into this section. So m plus this moment is coming due to the shear force, that is the F into the center point is there, the C point to this is dx by 2. So F into dx by 2 is the moment due to the shear force, plus you see on the other side you see this bending moment is there, which is coming from the other side. So plus F plus dF into del x by 2, from the C to this portion the delta x by 2 is there, and on this section you see this F plus dF is going in this direction. So you see it will be in the minus way. So this plus F plus dF into dx by 2 is equals to m plus dm, which is in the counterclockwise direction. So meaning is pretty simple, that you see here, if we have this element, and if all these the moment as well as the shear forces are acting, first of all what we need to say, we need to assume that under the application of these all forces, our total element is in equilibrium position, and once it is in equilibrium position, whatever the forces which are applying on those things, they are supposed to be balanced irrespective of whether the forces or the moment. So here you see we are just going with those conditions, and we assume that since it is a balanced part, so what we have a balanced moment condition. So either the moments are coming due to the real bending moment, or the moments are coming due to the shear forces, they must be well balanced and they must be interact like that. So this equation satisfied that condition, and now you see again by cancellation these m, and by manipulating those things, what we have F into dx by 2 plus F plus. So we can see that the moment is simply cancelled out by both of the way. So we have this equation F into delta x by 2. So on the left hand side, whatever the moment is coming due to the shear force, it is there, plus the right hand side moment due to the shear force F plus dF into delta x by 2 equals to delta m, because m has cancelled out. And now we know that whatever this thickness which we are considering here in terms of delta x, or the delta f, they have a very less impact on these moment equations. So what we need to do here, whatever the multiplication is coming because of this delta x and delta f, even their impact is very less. So we can simply neglect those terms. So you see here what we have after doing this particular, say that neglecting the product of a small f and a small x because of the small contribution, or we can say towards the total impact, or we can say the towards the total bending moment or the moment portion also. What we have after concluding that part, we have F into delta x by 2 plus F into these delta x by 2 because of these forces, F into delta x by 2 plus delta F into delta x by 2 is cancel out, as I told you, equals to delta m. So you see if I cancel out this portion, then we have F into delta x by 2 plus delta x by 2, that means F into delta x, which is equals to delta m, which is on the right hand side portion. So you see if I am concluding that part for a small section where the shearing forces as well as the bending moment is applied, we have the final conclusion as far as this shear force and bending moment is concerned. F is equals to dm by dx, or if I simply apply this dx tends to 0, I have the shear force which is equals to the rate of change of bending moment in the x domain. That means, you see, what is that? Wherever the change of moment is there, it will simply apply the shear force on the section. So if you just remind those things from this equation, if you if from this equation 1, if you just remember that we have a cantilever beam, and on this particular beam we have the forces. The force application is there from the top of side and the force is coming from the bottom side. So meaning is that wherever the change of the moment is there with respect to x, it always gives you the shearing action, and whatever due to the shearing action the force is coming out, that is F. So we can say that F is nothing but equals to dm by dx, and it is a very good relation in between the bending moment as well as the shear force, because you see it is giving you a clear feeling that wherever the bending moment is there and wherever the change of bending moment is there with respect to this domain x, always the shearing force is appeared in that particular part, and we need to calculate the shear force by simply changing dm by dx. So you see, now again this kind of analysis came when we simply balance the moment equation. But now you see, if we balance the vertical forces, because you see, if you just remember the figure, then you will find that we have the vertical forces all along acting on the this bending this cantilever or the simply supported beam. So now if you would like to see that, since the load is coming from the top of side, which is at point C is W into dx. So this is the total load which is coming from top of side, and the shearing force, the forces which is, you see, are there from both of the side. One side which is F, one side which is supporting this part is F plus df. So you see, by balancing those conditions, what we have one side which is going upward direction, that is the shear force F, and on other side we have the shearing force is F plus df, which is coming towards downward direction, and also you see the one force which is coming due to the applied load, that is W into dx. So if you balance those things, W plus dx, W into dx plus F plus df will be equated by this force F. So F is equals to, if you see this particular condition, F is equals to W into dx plus F plus df, or you see, as I told you, whatever the conditions are there, if we balance those things, F will cancel out. So we have W equals to minus del F by dx, and you see whatever the the small segment which we are considering here, dx is, if it is tending to 0, then you see we have simply differentiate in a real manner. So we have W equals to df by minus df by dx, or we can say that it is minus d by dx of dm by, because F, you see, from this first equation we can simply replace this. So we have d2m by dx square. So the meaning is pretty simple, that whatever the load application is there, the load is coming on point C, so whatever the load application is there, the magnitude of this load can be easily calculated by the first derivative of the shear force with the x domain. So whatever the change of force is there in the x domain will clearly gives you that what the load application is, means what is the basic cause of this shear forcing is. So here the change of force with respect to dx will be equal to F. The negative direction itself, you see, it has a different meaning, that what the direction, according to which direction you are choosing, this minus sign will come. Or else we can say the second derivative of the moment with respect to dx will give you the load. So you see here, if you want to correlate, so that's what you see, our intention was, you see, that we just want to correlate the applied load with the shear force as well as bending moment. So the basic relation is W, which is the applied load, is nothing but equals to minus df by dx, or it is equals to minus d2m by dx square, which is a very important relation, because you see, from this relation, whatever the kind of beam is there, irrespective of simply supported beam or cantilever beam, only the boundary conditions are changing, or whatever the kind of loading is there, once you take the segment, or once you know that okay, this is the nature of the load, which due to this actually this shearing or the bending moment is coming, or this is the nature, you see, of the load, it is varying like that. Once you know these things, you can simply put in terms of the force or in terms of moment, and you can get the load. Or you can say that actually what the intensity of the load is there at the different points, like at x equals to 0 or x equals to 1, 2, 3, whatever kind like that, you can easily get those values if you put those values in this df by dx or this d2m by dx square, and if you can simply put those boundary conditions applications as well. So now you see we have the two basic conditions, two basic formulas I should say. Formula 1 which gives you the relation in between the shear force and the bending moment, and formula 2 will give you the relation in between not only in between the shear force and bending moment but also with the applied load. W equals to dF by dx, or we can say d2m by dx square, and minus sign is always you see gives the direction of these forces. So now we would like to conclude that part. From the above equations, whatever you see the two equations, the following important conclusions we can simply draw. First equation was which was correlating the shear force and the bending moment. So from the equation 1, the area of the shear force diagram between two different points, from the basic calculation we can simply calculate the bending moment. From that is bending moment is nothing but equals to integration of this f into dx. That means you see what is the intensity of the force is into, if you multiply with the total where this force is applied, means what is the affected this segment is there, you can simply get the bending moment. That means you see it's pretty simple that if you know the force and if you know that what is the point of application of this force is there, you have a bending moment. So always keep this in your mind that actually if a beam is under the various application of load, always bending moment is there, and it can be calculated by simply integrating the applied shear force or what is this resultant shear force into the distance, whatever the distance is there. The slope of bending moment is nothing but the shear force. That is the key part. If you know the slope of the shear force, that means if you have the value of m and if you just take the slope of that, you have the value of the shear force. Means you see if we have a f equals to 0, that means the slope of bending moment diagram is 0, the bending moment is nothing but the constant, or we can say from the first equation f equals to dm by dx. If I know that the slope is 0, that means dm by dx is 0, we have the 0 shear force. Means you see if there is no slope, that means if you see the projection of this particular bending moment on this cantilever beam is 0, then you see there is no shearing is occur in between due to these particular forces, they are simply counterbalancing. That means there is no eccentricity in between these applied and the reactive forces, and the maximum or minimum bending moment occurs always when dm by dx is equals to 0. So that's what you see we can simply get, just remember these conditions, because whenever we apply this condition on either shear force or bending moment diagram, these are real applications for calculating these parameters. And then you see the last part, the slope of a shear force diagram is equal to the magnitude of the intensity of distributed loading. Just keep this thing in mind, whatever the slope is there you see of the shear force diagram, because the slope of the bending moment will give you the shear force, but the slope of a shear force will give you the magnitude of the intensity of the distributed loaded at any position of the beam, and whatever the sign is coming, the negative sign is simply a consequence of our particular choice of the sign convention. As I told you, like if you want to calculate W, which is nothing but equals to minus df by dx, or W which is minus d2m by dx square, minus is always there, that how you are considering the sign convention or how you are considering the load application on that particular beam. But the important thing is that actually what is the slope relations are there in between the intensity of the load with the shear force, or between the shear force and this slope of the bending moment is always gives you a clear cut value, and it gives you the real feeling of bending moment as well as the shear force diagram, the shear force. So you see here in this chapter we discussed about that if a beam is under the application of the loading, always you see we found that the shear force is there, and also we found that actually the bending moments are there. And here we in the last section we found that there is a straight relation in between the load application, shear force and the bending moment. And also we found that we can simply get the sign convention by just watching that how these forces are acting on a beam. If you see the two forces are acting on a beam, and they have on the left hand direction, if they have the resultant which is going on this upward direction, and in the lower direction if you see my sign this hand notations, this is the positive shear force and this is the negative shear force. Okay, so just keep in this in mind, this is the negative shear force. If these two forces are just going in this way, the negative shear you need to consider. If they are going in this way, it is the positive shear force. And then as well as the same sign convention which we discussed, that if the bending moment is the slagging part is there, if the bending moment is going in this way, means if beam is going on the bending side in this way, slagging portion we have a positive bending moment, and if it is going in this downward direction, the towards this clockwise and anti-clockwise direction, like we are saying that this is the negative bending moment. So this part we discussed, and in the next like lecture we would like to discuss that if we have like the real numerical values, that if we have a beam which is under like the point load, or if we have this uniformly distributed load, or if we have a simply supported beam or a cantilever beam, then what exactly these theories are applicable, how we can calculate like this shear force and bending moment. And also after calculating these values at a different points, we would like to draw the shear force diagram and bending moment diagram to have a clear feeling that what the variation is there of the shear force and the bending moment over the entire length of a beam if this beam is under the application of variety of the loads. So you see here, like in the next lecture we would like to discuss this kind of issues. Thank you.